So I welcome you all here. So it's my great pleasure and honor to introduce Professor Detlef Lohse, who happens to be a great mentor and a very close friend. So Professor Lohse got his PhD from University of Marburg, working with Professor Siegfried Grossman. Then he did his postdoc in Chicago, working with Professor Leo Kardanoff. And Detlef currently leads one of the most vibrant physics of fluid group in the world, where the research interest lies across the scales. So it's starting from both from nano and microfluidics all the way to geophysical flows and turbulence. It's also it's also a safe haven for young researchers such as me and several others who love to be there and discuss fluid mechanics with Detlef and everyone else. Detlef also has worked quite a bit on physiochemical hydrodynamics, and it's one of his has published several papers on that as well, along with multi-phase flow, free surface flow, wetting phenomena, and drop evaporation. If I were to start telling you all about Detlef's achievements and awards, I would probably need another half an hour. So I'm not going to do that. I will just mention a few notable ones. He received the Max Planck Medal in 2019 and joined the select group of people such as Albert Einstein and Max Planck, who we all know to be household names here in India as well. He was also awarded the Fluid Dynamics Award from APS and the Bachelor, the GK Bachelor Fluid Dynamics Award as well. He has authored several publications, 500 plus, in notable journals, including Journal of Fluid Mechanics, where he has published close to 150 articles, and Physical Review Letters, where it's close to 100. Detlef is also, he really encourages scientific outreach, and I can attest to that. And as a result, being an associate editor of Journal of Fluid Mechanics, he has taken several steps to ensure that. And as a group, we always try to work for scientific outreach, and as a result, we submit quite a few videos to Gallery of Fluid Motions, which we happen to win more than 10 of them. So as Detlef always says that life is in life, the most important thing is science, and everything else is just background noise. So I'm going to shut myself off. I'm going to shut this background noise off, and I will leave it to Detlef to tell you all about impact of droplets. So Detlef, the floor is all yours.
Well, thanks a lot, Ratzel, for the nice introduction, and good afternoon to everybody. Unfortunately, I cannot be there because I'm in Santa Barbara right now. So for me, it's Thursday evening, and well, I'd love to be over there, but we have a geophysical program here, which I greatly enjoy, so I cannot be over there. So, but I can do it remote, and the subject is impact of droplets. And first of all, let me show you the co-workers. So the main co-workers are in boldface, and this is Vatsal Sanjay, whom you see over there, and Pierre Chantelot, and then Kunjing Liu, and Bin Zhang, and various other co-workers over the years. And I also give some funding information. So here I show you drop impact, and it's drop impact on paper. We all have seen this phenomenon. This impact looks pretty different once we go for impact of a droplet on cotton. This is what you see here, very different behavior. And the liquid, in fact, which you see falling on cotton is blood. So this was a little experiment we did for the Dutch Forensic Institute. And well, it was a very interesting outcome here. Here you see drop impact on a super hydrophobic surface. On the left with low velocity, and you already see that there's some bubble entrained. And on the right, you see with impact with very high velocity. So the relevance of drop impact is huge. So I showed you examples in the forensic context. I showed you examples for self-cleaning materials on super hydrophobic surfaces. The most famous example is, of course, inkjet, and not only for graphics, but way beyond. So here you see an inkjet printer drop on demand from Canon, with whom we collaborate. So, well, with this machine, you can print a book within less than a minute. Václav, there's quite some echo, so I hear me twice. I mean, it would be good if somehow the echo could be turned off. So perhaps you put this computer on mute, and later when we have questions, you can unmute again. Good. So the core of this printer is this print head here. It's MEMS based, and each printer have hundreds of these print heads, and each print head has, in fact, thousands of these nozzles. And with this, very high printing quality can be achieved. The core of this printer is this principle. You have electrical signal, which is transferred into some mechanical signal with this piezo. And this piezo builds up some pressure in this ink chamber, and the drop is then flying out of this chamber towards some substrate. And here's the impact, and this is what this talk is about. Here you see an example of this drop generated, and it's visualized with stroboscopic techniques. It's a beautiful drop, and so the collaboration was applied. This picture made the competition Nature Picture of the Year, so we were very happy that it was chosen, and it shows that good application and relevant applications and good science are not a contradiction at all. So here you see the phase space of inkjet printing, the Reynolds number here and the Ohnesorg number here. So the Ohnesorg number basically represents the viscosity, and printable liquid is only in this very small green range. This green dot is what you have just seen. So here you have insufficient energy for the drop formation. Here it's too viscous to be printable. Here you get satellite droplets, and here you get a splash. So all this you don't want, so you want to be here. So it's a very small range in parameter space. So apart from these three examples, there are many, many more applications, and I will only flash a few ones. So you have spray coating here. This is a machine which spray coats cars. You have spraying pesticides, which you see here. You have spray cooling, mainly for the steel production. And you have medical applications here. There's a nozzle for med spray. So all create droplet and droplet impact. So here I give more examples: additive manufacturing, agriculture, spray cooling, XUV lithography, icing, climate models. So drop impact plays a major role in the coupling between the atmosphere and the ocean, then in diesel engine, combustion, and in diagnostics. So it's all over. Here I give you an idea on the parameter space of inkjet printing, and the velocity here over 5 orders of magnitude, and the inverse size of this droplet, the inverse diameter here, over 9 orders of magnitude. So here you have rain, you have diesel engines, inkjet printing, thermal spraying, and all kind of applications. So you see it's a huge parameter space which you have. But it's not only those two parameters. So apart from velocity and diameter, it's also viscosity, density, surface tension. It's the roughness of the surface, as we have already seen. It's the temperature, and it's even the ambient pressure. And I will come to this in a second. So here you see the impact of the ambient pressure. This is a famous experiment from Sid Nagel's group. On the left, you have 1 atmosphere. On the right, you have 0.2 atmosphere. And on the left, you see some splash. On the right, you don't. And the reason is the air. And, well, I will show you in a second why this is the case. So let's look at this dimensionless control parameter space of the droplet. So I already showed diameter of the droplet and the velocity here on the super hydrophobic surface. And then you have surface tension here. You have the viscosity of the droplet, you have a density, and also outside, you saw air is important, you have the density of the surrounding and the viscosity of the surrounding medium. And out of this, you construct a Weber number for the droplet, and you construct an Ohnesorg number for the droplet, and then you also construct a Ohnesorg number for the surrounding, and as additional parameter, you also have the ratio between the densities. So all these are dimensionless, relevant dimensionless parameters. And I will focus in the first part mainly on those two, Weber and Ohnesorg. So when you now go in the dimensionless parameter space, Ohnesorg versus Weber, I only give 3 examples. So here you have rain, small Weber, and small Ohnesorg number. Inkjet printing is up here, so larger Weber number and larger Ohnesorg number here. Well, here you have this jet drops from bursting bubbles. So those drops which emerge when a raindrop falls on water, and you get this jet. So they are here. And you can also go to alternative dimensionless numbers. So rather than Weber and Ohnesorg, you could go to the Reynolds number, which I showed before. You could go to the Stokes number here, which in fact represents the ambient air, or you can go to capillary number. So, but they're all dependent on Weber and Ohnesorg and on the density ratio. So where will this talk bring you? I will first answer the question, why is the ambient pressure relevant? Then I will come to drop impact on superhydrophobic surfaces. And then I will answer the question, when does the drop stop bouncing? And then I will go to superheated surfaces and show you something about the Leidenfrost effect. And then if time allows, I will show you the breakdown of the Leidenfrost effect as a direct percolation phase transition. So first on why is the ambient pressure relevant? And this is what you see here. So this is impacting droplet. And you see just before the droplet is touching down, there's a pressure build-up under the droplet. And this pressure build-up deforms the droplet. So you get this dimple formation. And we visualize this dimple with ultra-high-speed color interferometry. So here you see the picture. And out of this picture, we get direct information on the thickness of this layer. So this is we do in this way with interferometry. So light is coming, light is reflected here at this glass-air interface, and also it's reflected at the air-gas interface, and you get interference phenomena. And out of this interference, you get information on the thickness and how it depends on space and on time. The experimental setup is very easy. You have a droplet falling down, and you look from the side, and you look from the bottom, and out of this, you get this information. So it's crucial that you have a colored bottom view, because you have color interferometry. And this is what you see at the top, the side view, at the bottom view, and you get these rings, and out of this, you extract the information. And here you see the information on the height. So you see with this interferometry, you get a resolution down to micrometer. So it's a micrometer deformation, and the dimple has a height of about 3 micrometers. So this here is millimeter. And this is extracted from pictures of this type. It's totally reproducible. So here we have 3 experiments. It's absolutely sitting on top of each other. So each single wiggle here is represented. And no, now you would like to understand it. And in fact, we can understand this quantitatively. So what we do is that we do a bound integral calculation for the droplet itself, simply solving Laplace equation and the unsteady Bernoulli equation. And we get then the profile H of R and T and the pressure as a function of R and T. And we must solve for this. But to solve for this, we need a second equation. And the second equation, in fact, is the viscous lubrication approximation of the Stokes equation. Viscous because the gap between the droplet and the substrate is so thin that the Reynolds number is very small. So it's gas, you can use the viscous lubrication approximation. And those two coupled PDEs you can solve, and what you get are pictures of this type. So here I show you the height as a function of radius and time. This is the experimental picture, and it's totally reproduced by what we see. There's no parameter in this. And here you see the height of this dimple here and the height of the lowest point. And the question is now, yes, we get a bubble entrained, but under what conditions is this entrained bubble maximal? So for large velocity, or for large droplets, you have lots of inertia, and then the impact makes a very small dimple. It's simply the mass smashing against the surface, and you don't get much of a dimple. For small velocity, in fact, the capillary forces keep the droplet together, and the droplet is always ground, and you also have a very small dimple. But in between, you have a maximum. And this is now what the results are. What I show you is the size of the entrained bubble under the droplet, normalized by the size of the droplet versus the Stokes number. The Stokes number is the inverse, is basically the velocity here. So here you see it in terms of impact velocity, and here in terms of volume in picoliter of this bubble. And red is experiment and blue is simulation. And there's, in fact, not a single parameter there. So on the left, we have the capillary regime. where the capillary forces minimize the bubble. On the right, we have this inertial regime, and in the middle, we have, in fact, this maximum, which perfectly agrees with experiments. So for a millimeter droplet, in fact, is about 20 centimeters per second. And this is exactly where you normally are in experiment. And that's why you, in experiment, get this large entrained bubble under those droplets. But, well, what happens at larger viscosities? So I told you that we use bound and triggle, but when you have larger viscosity, you don't get away with this. So bound and triggle is no longer possible because potential flow with large viscosity is inappropriate. And also, the lubrication approximation at some point will no longer break down, and direct numerical simulation of both the droplet and of the surrounding gas are required. And fortunately, over the last years, Stefan Popinet and his colleagues have developed the volume of fluid method with Basilisk, and there's wonderful open software on this. And Watso has a sandbox on this Basilisk page, and well, you can scan and go there. It's a great software and kept by the whole community. Well, many people, among them Watso, contribute to have this state-of-the-art software with great precision. And this we use. And with this software, we would like to answer with combined experiment the question, what are the forces exerted on the substrate? So I showed you this movie before, impact on superhydrophobic surface with this entrainment. This impact, of course, will exert a force on the substrate. So what is this force? And what we will do is that in parameter space, we will first go in this direction. This is basically a water droplet of a millimeter size, and we will increase the impact velocity, so basically the Weber number. And under this condition, the Ohnesorg number is 0.0025. So this corresponds to water, so it just goes through this grain regime here. And we will see what's going on. And here I show you a Basilisk simulation, and I will show you various of this. This is for a case where the Weber number is 40. And on the left, I show you the local energy dissipation rate on a log scale. And on the right, I show you the velocity, the modulus of the velocity. This gives you this color code. And this impact shows you first the impact, then you have the spreading, and you have the recoil and the takeoff, because it's a superhydrophobic substrate in this case. So here it takes off as a whole, and here it splits off. And we now want to analyze the forces exerted at this impact. So how do we measure the forces? Well, it's pretty easy, in fact. You put a precise force sensor under your substrate, and with this you measure the forces. And in numerics, it's also easy. You simply integrate the pressure over the area, and with this you get the force. So on the left, you see the numerics, and on the right, on the left, you see the experiment, on the right, the numerics, and you already see that the agreement is pretty good of these two events, but of course you would like to see better. And this is now the force as function of time, and red is simulation and blue is experiment. And what's flabbergasting is the degree of agreement. So isn't it amazing? I mean, every single wiggle which you see here is reflected in the numerics. And that's the first surprising thing, that the agreement is so good, and this can now be achieved. I think 20 years ago, nobody would dare to dream about this. And the second surprising result is the second peak here, because we would all expect this first peak when the drop falls on the substrate, but there's a second peak. And I will show you cases where the second peak is, in fact, even larger than the first peak. And I will now explain these two peaks in detail. So let's look at in detail what sets the size of the peak and the force, why, when do they occur, what time, and how do they depend on the Weber number. And so the first peak is exactly at impact here, and that's this peak F1, and that's very well known. In fact, this is the annual review of fluid mechanics by Leonardo Gordillo, and that's here the inertial term, so that's very well understood. Here you have the force as function of Weber number. There are some capillary corrections here, but for large Weber number, it is simply this inertial impact, which you would directly expect also from dimensional analysis. So capillary regime here and the inertial regime there. So this is not so special, but what's special is the physics of the second peak. And this occurs at the recoil. So the droplet falls on the substrate and recoils and takes off. And at takeoff, you get this recoil, and this leads to the second peak here. And then here you take off, and off it goes here. And well, the time of this event is T3. So at T3, it takes off. So the synopsis of this impact is seen here. And the questions to ask are, how do these numbers, so the forces and the times, depend on the Weber number? And I can't answer all this. The answers are found in our recent PL, which came out earlier this year. What I will talk about in this talk is how this second peak depends on the Weber number. So there will, in fact, be 4 different regimes with increasing Weber number. So here I show you the strength of the second peak as function of Weber, both in experiments and in simulations. And let's start with very gentle deposition, and then its capillarity dominated. In fact, it's so gentle that in experiment you can't do it. In the numerics, fortunately, you can do it, and you get these capillary oscillations, and the first peak is not pronounced at all because you really very, very gently deposit this droplet. And you get here the force as function of this Weber number. You get some scaling, which you understand. I can't go into this. And this scaling even goes beyond this regime 1 towards regime 2. And here I compensate, in fact, with the inertial expectation. And here on the right, I compensate with the capillary expectation. So you see that up to here, it's all dominated by capillarity. However, you see this very strange peak here. And this is about at Weber is 9. And the question is, what's going on at Weber at 9? And in fact, there is a singular jet. I will now show you the simulation as Weber is 9. You see, after the first peak, you get still capillary waves, but then you get this bubble forming here. So this bubble closes, and once you have a full closure of this bubble, you create a jet. This air cavity and a jet, and this jet originates from the closure of this cavity, and there's in fact a jet down, which exerts this second peak, and a jet upwards. And automatically you get this entrainment of the bubble. So on the left, you see this entrainment of this bubble, and the phenomenon is so spectacular. It's really a singularity which arises here at this particular Weber number of 9. And then it takes off, and you see that a bubble is entrained. This is exactly the movie what you saw at the very beginning. You get entrainment, both in experiment on the left and also in the numerics on the right-hand side. So here you see the synopsis of this regime with this spectacular second peak, which in this case is larger than the first one, in fact, 3 times larger than the first peak. And how wide is this regime? Well, it's in fact pretty narrow. We show now 2 simulations at Weber is 5 and Weber is 12. This is what you see here at the top row and at the bottom row. And you see in both cases, there's no entrainment. And the peak is much less pronounced, the second peak. So it's a very narrow regime. It's very typical for the singularity, entrainment of this bubble and this pronounced peak at this particular Weber number. So in regime 3, things are inertia dominated. This is for Weber number between 30 and 100. This is this regime right here. And you see when you now compensate your force with the inertial expectation, you get this straight line. And here I show you 2 cases. At the left, Weber is 30, and on the right, Weber is 100. You still get, in fact, this pronounced second peak, but you don't get entrainment. And then finally, you get this regime 4, and there you have droplet fragmentation and splashing. This is for Weber is larger than 100. And now, for the first time, we see a disagreement between simulation and experiment. The reason is that the simulation are axial symmetric, whereas the experiments are, of course, not. And here the droplet disintegrates. But nonetheless, looking at this comparison is very illustrative. So here it's still amazingly good, but at some point, of course, you get disagreement because the axial symmetry is kept here on the right, whereas in reality is lost. So the summary for this very small Ohnesorg number of water droplet impact is you have excellent agreement between experiment and numerics. You get 2 peaks in the force. You get 4 different regimes in Weber number, and you get this singular jet and bubble entrainment at the singularity of Weber and Weber of 9. And the dependence on the Weber number is very well understood, not only of the peaks, but also of the times. I didn't have time to go into this. And this came out, as I said earlier, this year as editor suggestions in PRL, and it was also highlighted in research highlight in Nature. And well, here you can download the references. But this was a water droplet. Now, what's the effect of this viscosity? So all these forces and times depend on the viscosity, so on the Ohnesorg number, and I will now briefly address what happens to this second peak here. How does it depend on viscosity? So here is what I showed you before for water, the first peak with the capillary regime here and the inertial regime here, and I will now increase the Ohnesorg number both in experiment and in numerics, again, perfect agreement, and up to Ohnesorg of 0.2, in fact, you see that not much changes. So this capillary regime and the inertial regime are pretty unsensitive to Ohnesorg numbers up to about 0.2. So it's independent of Ohnesorg number. Of course, when you go to extremely viscous droplets, the Ohnesorg number of 2, then those forces increase. And this is what you see here. And the good way to look into this is not to go along those curves in parameter space. This is what I showed you up to now, but to go up here in parameter space. So we pick a Weber number of 10, and then we look what's the Ohnesorg number dependence. And then we see that down here, indeed, there is no dependence, but when you go up to very large Ohnesorg numbers, you get this very, very strong dependence. And here I show you 3 cases. Ohnesorg is 0.01. This is the case you saw before. Ohnesorg is 0.5. This here is at the borderline between this regime and this strongly damped regime. And then Ohnesorg number is 5. The drop is so viscous, basically it's stuck there. So this is what you see here. And when you now change the Weber number, you basically see the same phenomenon also for larger Weber numbers. And the scaling here is goes like square root of Ohnesorg number. And I'm sure it can be derived. We haven't done so yet, but I'm sure it can be derived from balances. This is all brand new work. Well, we see this scaling with square root of Ohnesorg number, and we are now about to derive this. Well, what about the second force peak? I showed you the first force peak, but what about the second force peak? And you saw this singular jet at Weber is 9 at the small Ohnesorg number on the left. But when we now go to a slightly larger Ohnesorg number, only a factor 2 larger, you see that this entrainment of the bubble is gone. No bubble anymore. So I play this once more. On the left, we have this entrainment of the bubble. On the right, we don't. So we see it's a very sensitive thing to have this entrainment of the bubble. And in fact, when we now go to even higher Ohnesorg numbers, so now another factor 10 up, we see that also the jet is gone. And so the second peak is extremely sensitive towards the Ohnesorg number. So viscosity totally destroys this singularity here. Very different behavior from the first peak. Well, the question is, when does this drop stop bouncing now? And well, you can have too large viscosity for the bouncing. This is what you also saw when we went to this very high velocity. And already in this paper by Chantelot, Clanet, and Queret, well, they showed that once you are beyond a critical Ohnesorg number, that then you don't get bouncing anymore. But there's another way to get to an end of this bouncing. And this is too much gravity. Well, gravity you can't change, but what you could change is the bond number. So when we now increase the bond number, simply everything is then dominated by gravity, and the droplet is in fact pressed so strongly against the wall by gravity or against the ground that it cannot get up again. So it's clear that if gravity is too strong, the drop can't go up. It's too heavy, so to say. And here we see the transition. On the left, bond number 0.4, where it still takes off, and on the right, bond number 0.8, where it doesn't take off anymore. So in between, there is this threshold from the bouncing to no bouncing transition. And of course, you would like to understand this, so need a criterion. And we calculated this from balancing potential energy and dissipated energy on the one hand, and this must be balanced by the surface energy. And well, this here G enters, here eta enters, and here the surface tension gamma enters. And out of this, from this balance, you get this very simple relation that the critical Ohnesorg number for the droplet plus the critical bond number must be order of 1. So that we pretty strictly derive. And this is what we get in parameter space. Bond number here versus Ohnesorg number here. This regime is bouncing, and this is non-bouncing. And those data point are at this threshold from bouncing to non-bouncing. They're exactly on our curve. So this curve is what we calculated. Well, here we have for other Weber numbers, we have the data. And this paper, in fact, I just got a mail from Watzel. This paper has been accepted in JFM today. Here you see the reference. Well, this is still on archive, so here you can go and download it. This is now, so to say, JFM in press. And the fourth subject I would like to address is impact on superheated surface. And that's work we started about 10 years ago with Tuan Tran. As a postdoc, he is now professor in Singapore. And I show you what we do. So the influence of the surface temperature. On the left, the surface temperature is 200 degrees. On the right, it's 300 degrees. At 200 degrees, everything is boiling away. And the lifetime of the droplet is very small. Whereas on the right, the droplet is supported by its own vapor. It doesn't touch down. And therefore, there's a very weak coupling from the substrate towards the droplet, and the lifetime is very large. This phenomenon had been found by Johann Gottlob Leidenfrost, whom you see here. He did experiments exactly of this type, what I show here, a hot spoon and a droplet on there. And you see the floating drops supported by the vapor layer. You also see the dimple here. And there's a beautiful review, an annual review of fluid mechanics on Leidenfrost droplets by David Queret, whom you see here. The lifetime at the Leidenfrost temperature increases. This is what you see here, the lifetime of the droplet as function of temperature. And here you see this jump. And here, for this particular condition, this is identified as Leidenfrost temperature. And we are now interested in the dynamic Leidenfrost effect. So up to now, we gently deposited the droplet on the substrate, but now we let the droplet fall on the substrate. My talk, after all, is on impact. So we let this fall and look from the bottom what's going on. And we get different boiling regimes. So we either get contact boiling. This is what you see here. The impact is so strong and the temperature is so low that you get contact. So this black stuff is contact. And when you go to higher temperatures, you get gentle film boiling. So no real touch down. So it really doesn't get black, and it's floating on its own vapor. And no contact. So this is what we call the dynamic Leidenfrost state. And when we go in parameter space, we see here the contact boiling and the transition towards the Leidenfrost state. The blue is the Leidenfrost state. That, in fact, goes up with increasing velocity. So it's clear that you can have much more contact for high velocity. So you must heat things up much more when you have high velocity. So this is this transition between these two regimes. What you also get is a third regime. This is a spraying film boiling regime. And this is what you see for very high velocities and for very high temperatures. And what's happening there is that, in fact, the droplet spreads so much that it boils as a whole and can create little bubbles. And these bubbles, these collapsing bubbles, lead to the spray. So then you get, in fact, phenomena of this type. It's spreading. It first looks like standard Leidenfrost, but then you see all these droplets coming out of this puddle, and those originate from these collapsing bubbles. So we call it spraying film boiling.
So
and this is up here in this regime.
So yes. You have 5 more minutes if you want to leave for questions.
Yes, so maybe I will do that, yeah.
Yes.
So we have 3 scenarios in comparison: contact boiling, gentle film boiling, and spraying film boiling, which you see here in comparison. And is this the full story? No, it is not. We can go even closer. We have total internal reflection, and there we can resolve, in fact, down to a few tenths of nanometers. This is what we see here, the total internal reflection. This is FSC 84 on sapphire, and now on glass. We see this film forming, and this film creates this instabilities here, and it's bursting, and it's extremely rich dynamics. So here you have transition from contact boiling to film boiling, and what you see here at 25 degrees is that this lamella exactly shows you the area of contact, whereas at high temperatures, here, this is not the case. You get takeoff of the lamella. So the red shows you the area of touch down. This is the contact area, whereas the blue shows you the lamella. And you are, in fact, in this transition boiling regime, where you have contact in the center, but take off at the edge. So out of this TR pictures, you get quantitative information. So the top is a side view. At the bottom, it is a bottom view. And you see here now the information on the contact. So red is contact, blue is far away. At 150, you have full contact, but at 170, it's partially boiled away. And at 180, it's fully boiled away, apart from at this rim. And this rim here that you had seen before. And well, if you go to even higher temperatures, there's no contact whatsoever. So you get this phase diagram for this case with contact boiling down here, transition boiling here, and Leidenfrost boiling up here. The question is, how does it depend on the liquid? And you see on the left the diagram for ethanol, on the right for FC84, and you see the Leidenfrost temperature here is much, much lower. What's the difference? Well, it's in fact the latent heat. So for ethanol, the latent heat is relatively large, whereas for FC81, it is much smaller. Therefore, you get this Leidenfrost state here in red. You get much, much earlier as compared to ethanol. And what is the effect of the substrate when you now compare glass and sapphire? So here I show you things on glass, and you already see that the impact looks a little bit different as compared to the impact on sapphire. You have a delayed touchdown. And the delayed touchdown, in fact, is a cooling effect. So when the liquid is evaporating, it takes out heat, and because glass is not perfectly thermally isolating, you get a cool down effect. So here, when you look at the Leidenfrost temperature on the left with glass, it's much higher than on the right with sapphire, and the reason is that this is no longer isothermal. The relevant temperature, the relevant timescales you can estimate. In fact, this has already been done in the 60s and in the 70s. The crucial parameter is the comparison of the thermal timescale given by the conductivity of the substrate and the dynamical time scale given by the impact dynamics. And to get a cooling effect, this dynamical time scale must be larger than this thermal time scale. And when we now compare these data in experiment, we see for glass, for these parameters, this is not the case. So for glass, you have cooling, whereas for sapphire, you don't have cooling. And so that's consistent with these observations. And with this, I would like to end. So as anticipated, I didn't make this last subject here. So let me go through this very, very quickly. I didn't make this as anticipated. And I would like to end with this. Where does the talk bring you? Well, there's 4 subjects. Well, the breakdown of Leidenfrost, unfortunately, I didn't make. And I show you this summary here of these various impact scenarios. And with this, I would like to end and acknowledge again the co-workers on this project and show you those beautiful movies. And I'm happy to take questions in my last 5 minutes.
So let's thank Detlef once.
Hello, I don't hear you.
Oh yeah, we just thanked you, Detlef. So
Recording stopped.
okay, we can do it one more time. Do you hear us, Detlef, now? Yeah.
I now I hear you again, but I didn't hear questions. So
Okay, yeah. So let's Rajneesh, yeah.
Thank you, Professor Lohse, for a very interesting talk. I'm Rajneesh Bhardas from IIT Bombay. My question is related to the first part of your talk. So you showed a nice universality in the phase space of honor source number and Weber number, but I was surprised to see that the wettability or the contact angle was not very important. So any comment on how this universality would hold for partially wetting regime or total wetting regime?
well, I mean, here we have a substrate which is super hydrophobic, and there in the numerics we don't have to deal about the contact angle. It's simply 180 degrees. It's not wetting at all, and well, this of course helps the universality. Once we have some effect, stick-slip dynamics and pinning and so on, then you lose the universality, right? I mean, then it depends all on the substrate. I mean, this is why I showed in the beginning this impact on paper on the one hand, and then impact on textile. It looked very different, but then it's really determined by the stick-slip behavior and by contact line hysteresis and so on. So this universality you only get once you have this impact on the super hydrophobic substrate, so that the material properties don't enter into this problem.
Thank you. Yeah. More questions? Yeah. Here.
Hello, sir. Sir, when droplet impact on the hydrophobic or super hydrophobic surface, I have seen many times a singular jet forms, but after many times we have seen that 2 or more jet forms. So what is the reason behind that? Means singular jet formation or maybe 2 or 3 types of jet formations?
Well, I mean, here in the bottom right video, you see this jet, this singular jet, and I can also play this again. The jet you form once you are in the right parameter regime. Once you go away from this, I mean, if you're too viscous or if the Weber number is different, it vanishes. I mean, it's really a singular jet. It happens to be that for millimeter droplets and say a typical velocity, impact velocity, say of 20 centimeters per second or so, you get this jet, but it's not that you would have this at all parameters. I mean, we vary Ohnesorg number and Weber number and Bond number. We vary over a huge range of parameters, and it is not that you would always get a jet. See, I mean, when you're a little bit more viscous, the jet is killed, as I showed.
Okay.
Yeah.
Professor Lohse, I was just curious, if the droplet is charged, like, in electro spray kind of applications, how, your droplet impact will be affected. Am I clear?
I mean, I don't know whether I get the questions. So you ask about electrowetting or when you have also electrical effects or
if the
so
droplet is coming from a nozzle which is connected to a power supply and it gets charged electrically, like you have it in electro spray applications.
yes. Yeah, well, then it's well, I mean, you can get all kind of extra phenomena. So the droplet can be charged, and well, I mean, then it depends on whether there's also some charging of the surface, and well, it's simply yet another new parameter. Well, I showed this huge parameter space, which we have for droplet impact, and this would add yet another parameter, and well, this indeed matters. I mean, things would be quite different.
Okay. So is there any work on it? Because there are so many applications where the droplets are getting charged. Just I wanted to know,
No, one could extend these calculations to also electrohydrodynamics, and well, people did this. So, in fact, Michael Brenner did this in the 90s. He with his PhD student Moses Hohmann. I mean, they had several papers on electrospray, and it's a very relevant application. And I mean, these days with this basilisk code, you could also include this. We haven't done so, but it can be done, and I think it would be very worthwhile to look into this electrospray formation and to revisit what Michael Brenner and Moses Hohmann did in the 90s. Now with this wonderful basilisk facility,
So
this
Detlef,
volume of code.
Detlef, it's already included, by the way, just so that you know. EDH. So
Yeah,
electrohydrodynamics.
I mean, it's in the code.
Yeah.
But well, we haven't done the calculations, so but it's indeed it's included in the code already. Yes.
What we probably need is more careful experiments, like for these phenomena.
Yes.
Yeah.
Okay. Thank you, Professor.
Do we have one short question? Okay. If not, let's thank Detlef once again. And thank you, Detlef, for staying up late. I know you had a hectic day today, so I am sure that everyone loved it. And by the way, if you have more questions, just find me. I will either answer you or I will connect you to the person who can answer you, and I'm around in the conference. Yeah. So thank you, and I thank you all for attending. Yeah. Thanks.
Yeah, I wish you further a good conference.
Yeah. Thanks, Detlef. Oh, okay. So I think so the conference organizers would like to give a small token of appreciation to you, Detlef. Since you are not here, I am going to accept that on your behalf. Do you hear me, Detlef?
Yes, I hear you.
Yeah.
Well, thanks a lot, and it looks like very nice tea. And as Watzel knows, I like Darjeeling tea a lot. So it's well, thanks a lot. So
Yeah. Thank you, Detlef.
and I hope it will fit into your luggage, Watzel. So.
Yes, it will.
Yes.
Thanks.